I start? Okay. Okay, good morning. I will, like yesterday, start with a very brief review of what we did yesterday. So, maybe you remember yesterday when I gave the review, or when I reviewed what we did on Monday, then I said we kind of saw an argument which has the purpose of ruling out certain views or interpretations you could have. And the same is true for what we did yesterday. Of course, in a kind of stronger way, because obviously the argument is an extension of the original argument by Wigner. So its purpose is to rule out much more, or more at least, than what Wigner's argument ruled out. And just to summarize what this thing did, so maybe I will just here write the title yesterday to say that's the kind of the review part. So we saw an extension of Wigner's argument. And in some way this will be also the kind of condensation point where we will now, as we today will discuss interpretations or views on quantum mechanics, and we will always test them against this particular argument and see what they have to say about the thought experiment. So to have an explicit thought experiment is always useful because then the interpretations have to become concrete. They're not just making general statements. I really have to tell you where is now the problem. How does the particular interpretation avoid the contradiction? Because obviously none of the interpretations wants to arrive at the contradiction. So you can really test them in some way and see what do they say. Now, by the way, I should maybe at this point also acknowledge one of my co-authors who developed this argument, Rauchiger. And there is a paper that I wrote with her that will be put online, or kind of a document where you can read the details of the argument that I presented yesterday. Also, in case that I don't have time today to go through all the exercises or the solutions, you would find the solutions in that document that should soon be online, if it's not already online. Okay, so what was the argument? So the idea was that instead of thinking of agents as somehow conscious beings, as Wigner does, we just think of them as computers that we can program. So essentially, I would say we program agents, or let's say an agent. Of course, there will be many of them, but A, or maybe you should say any agent A, because there are several of them, to follow a certain set of rules. Maybe you should say to follow certain rules. That's kind of a good way to test the theory. So if you have a physical theory, the theory usually gives you a kind of set of rules that tell you how you should draw conclusions within that theory. And so if the theory is precise enough, you should be able to program a computer to apply the rules. And then you can test whether things work well. So that's what we here do with essentially the rules of quantum theory. So what were the rules that we would program into the agents? So one rule is the rule that I called Q, which is essentially just one could say a special case of the Born rule. So maybe I write it again in a bit detail. So suppose that A, this is now the general agent I call him or her A, applies the Born rule. And I think I don't need to now write out what that means. I said it yesterday. So the Born rule is the rule that usually gives you the probability of seeing a certain outcome. So you put into the rule the state you assign to the system and the measurement basis, and then you check the overlaps. And in particular, if the overlap, we only consider the case where the overlap is 1, in which case we would say that outcome occurs with certainty. And essentially one thing we program into the computer, into this agent, is that he applies the Born rule to a system, and he can choose which system, so to any system S around him. Maybe why I said around him, because he it may not be defined what it means to apply the Born rule to oneself. So I restrict that. And finds that outcome, I had this example, set equal something like blah, has probability 1. So this is now not stated very mathematically, but I guess you know what I mean. I just apply the Born rule to the state I assign to a system and see whether it has perfect or overlap 1 with a particular state. Then what should the agent do? The agent then A writes or outputs, or as I say, writes into his notebook the following statement. So in some it's just a statement. So using the theory means he writes certain statements. And the statement he would write is, I'm certain that set equal blah. And usually I was more precise and said at a certain time, because the measurements usually have a particular time when they are carried out. But I'm not going to write that here. So that's what we program into the computer. So in some way you don't need to know more about what agents are, rather than that they follow rules. So consciousness is now not an issue we need to discuss. But then you program a second rule into the agent, because obviously we will in these scenarios have more than one agent. And what we want to do is, and this was kind of the thing that I explained in more detail yesterday, we want to kind of see whether agents who describe the world can be consistent, and in particular if I describe an agent who uses the theory, whether then and what I can tell about the conclusions that this agent draw, whether I can promote them to my own conclusions. And in this language I would say if A, the agent A, is certain that another agent, and now you see, this is now all described in terms of these notebooks. So it's really something you could actually, again, program into the computer. That another agent A wrote into her, let's say, notebook, I, so I is now A prime, am certain that set equal blah. Then A can also, or also should also writes into his, so this is now A's notebook, I am certain that set equal blah. So I discussed this, by the way, yesterday with Scott Aronson, from whom you will hear more, and he said this should be called transitivity of knowledge. You could think of it like that in some way. So you can promote knowledge of others to your own knowledge, provided, of course, I mean, you see, all these agents are programmed with the same rules, and also programmed to know what the overall experiment is, otherwise this wouldn't make sense. So this is what we did essentially yesterday. And then what we concluded is the following: if we now consider a particular thought experiment which is set up in a slightly strange way, so you have agents in boxes who are measured and so on, then we arrive at the conclusion that, so our conclusion was there are experiments, so it can be, or it happens in some way in certain experiments, that the notebook entry of A, of the agent A, does not match, or maybe I should rather say contradicts the outcome, the actual outcome. So that was what we did. That was my small review. So this is something we can verify. At the very end of the experiment, we can go there and see what is written in the notebook of A. And we can see what is the outcome. And in the notebook we will find, in this particular case, we found agent W wrote into his notebook, I'm certain my outcome will be fail, but the outcome that we will actually have is okay. So that's what we did. So that's a summary. Are there any questions about this summary? Of course, I gave you some exercises. I'm not now discussing the exercises, but let me just ask whether this is kind of the overall view, what we did. So we said we have some rules, we program them, and we see the rules are problematic because they will give us at the end an outcome, which is that. Are there questions related to that? No? Okay. Now in order to discuss these rules, I prefer to actually say this is not really a contradiction at the end. If, let's say, if you have at the end of the day an agent who writes something into a notebook which doesn't match what you see. So you at the very end of the experiment, you check the notebook and you check the outcome and you see the two things don't match. This is not logically a contradiction. You could just say maybe this is acceptable in certain interpretations. And so I write down a third kind of rule, which I call S, and I will explain later why I call this S, which just says the notebook entry of A should match the outcome that he actually sees. I mean, that's a kind of reasonable thing. And now you can, if I write it like that, you can phrase this as a kind of theorem. And some people call these no-go theorems. So the theorem would say the following, namely that these three assumptions now, Q, C, and S, are contradictory. So that's kind of the conclusions that we saw. And this is now the starting point, because now this is a neutral formulation, so to speak. It doesn't tell you which of these assumptions is problematic. It tells you one of the assumptions that we made is a problematic assumption. And by the way, we have an interesting situation because Scott wrote me an email in the night, which is a very nice email. I really appreciate your answer, which, however, contradicts the opinion that all the rest in this room has, because I made a query about is the statement that one particular H and F bar makes about the outcome W, in your case you have different names, correct? And the majority says yes, this is what quantum mechanics should say. And this is exactly the statement where you say it's a problem. But so and I just said that for the following reason, not to play. I mean, I see your point. It's an excellent point, and we should discuss it. But the reason why I'm saying that is that indeed it's very. So what happens now in this sort of experiment is indeed people just disagree, and the reason why they disagree is because they have just different interpretations of quantum mechanics. So even those who say they don't have an interpretation have in some way an interpretation, because as I told you on Monday, quantum mechanics is a priori a mathematical formalism, and somehow we need to match it to objects that are in some way physical, whatever that means, but at least perceptions we have. If I see an outcome, then I need to match that to the formalism and ask, what does this now mean? How do I represent the fact that I saw this outcome in the mathematical formalism? This is maybe a very minimal interpretation, but it's still an interpretation that is relevant here. And so now what we are going to do today is indeed go through interpretations of quantum mechanics, and they will indeed give very different answers about what is wrong, what goes wrong in this thought experiment. And just to start with a brief overview, that you see that
Renata, do you want to discuss it now, or do you want to discuss it later?
Maybe a bit. Maybe I will first say a few general things, and then we can discuss that. Just to make sure I can at least make some point, because the discussion may take quite long.
Perfect.
By the way, I have this this joke about this. So we at some point 2 years ago designed this experiment to just discuss interpretations, and then we thought this is a good topic to be submitted to one of the conferences in our field, QIP. So I submitted it there, and I got a very nice review comment which said, this is an interesting argument, but it will cause endless discussion and therefore should be rejected. That was the kind of most amazing report I ever got, but I don't know really what to make of it. Anyway, so now we will do this. And you can now see why there are these endless discussions. So just to start, there are certain, I call them extreme variants. And I will explain what that means. And I think this will be helpful for the discussion if I say what the interpretations say, because it gives a little of many worlds. There are sometimes, some people call these no histories, or it's sometimes called the no histories slogan. So they're kind of variants of many worlds where, informally speaking, you have no persistence of branches. So we are now in a particular branch of the wave function, and a second later we are somewhere else, and there is no connection between the branches over time. So essentially, there is nothing that kind of connects me now to the future. And that's kind of, they deny, or they violate S, this assumption. That's why this was actually the reason why I put this as an explicit assumption. In what sense do they I will come back to that in more detail, but essentially what they are saying is that, of course, it can be that I make a prediction which says the outcome is fail, but the outcome is actually okay. But why should I be worried? Because I know this prediction wasn't wrong. It was maybe, I should just interpret the prediction as a prediction about a different branch. So of course there is another branch in which the outcome is maybe fail, although I saw here okay. So somehow in this extreme variant you can say what happens in this thought experiment is that at the end of the day you can convince yourself there is another branch in which you saw the opposite thing. Of course, what this means, if you think about this, means that at the end it's useless to make any predictions, because whatever prediction you make, it doesn't match what you see in that branch. So it's just somehow you always predict other things that can also happen. So in that sense, it turns many worlds into a non-predictive theory. It's not wrong, it's not contradictory, but it's also not particularly useful to have a theory which tells you that whatever, if I, for example, predict that because I'm now in this room, I will still be in this room 2 seconds later, if that prediction doesn't hold, and this is indeed a prediction that wouldn't hold in this extreme form, because there is of course another branch of the wave function in which I'm not in this room, then it's very hard to give any meaning to predictions. So I started with that thing because there are not many, I think there are no other interpretations that violate this thing here, S. But there are interpretations such as, I mentioned many times, cubism, and I will come back to that as an example. Also, there's an interpretation called relational quantum mechanics by Carlo Rovelli and others. There's also something called consistent histories. And it has sometimes different names. So, for example, Bob Griffiths developed that thing together with others. And they violate C. So if you apply these, if you study the experiment in these particular interpretations, you will see that this rule C, so they would say we shouldn't program your agent to follow rule C. And then, let's say, for example, collapse series. Okay, I had a whole list I wanted to make, but I wanted to exclude at least one of them. Yeah, let me for the moment only put collapse series here, but there will be others we are going to discuss. Violate Q. So this is pretty obvious. So what does that, by the way, mean when I write these things? So and this line and this line. So if I now ask a person like a cubist to say, I go to him and tell him I programmed a computer to be a to be an agent in quantum mechanics, and I programmed him, this computer, to follow these rules. Do you agree that this matches your view on quantum mechanics? Are these rules in agreement with your view of quantum mechanics? Then a cubist should say, no, I'm not happy with these rules. You have to change them somehow. And Similarly, of course, a collapse person would say, no, for example, this rule, you shouldn't program it like that because there's something different. The Born rule doesn't always apply. So that's what it means. So it's really, it's now no longer, I stress that because sometimes people regard this as a philosophical question, but now it's a very practical question. You program a computer to follow the rules of quantum mechanics, and in order to program the computer correctly, you have to actually make your mind about which interpretation you have. And the program you will actually write will be a different one. So in this sense, it's no longer just, as some people say, it's no longer just a philosophical question. It's a real physical question about how to correctly program an agent in quantum mechanics. That's one of the main messages here, because foundations is often seen as a very vague thing. So this is extremely concrete. It's really about what you program into your computer. Yes?
Where does the correct interpretation many worlds go on this list?
Aha, so okay, now, yes, that's a good point. Thanks for, so I said here, extreme variants of many worlds. So where is the kind of more usual variant of many worlds? It will be essentially here. I would say so, and I will just explain that in a bit more detail. So indeed, what it means is that a many worlds, a normal, a non-extreme many worlds person. I mean, most people I know who follow many worlds are more here, like let's say David Deutsch and so on. They would say, indeed, I shouldn't program the computer according to this rule. I have to change it in some way. And now I'm going to discuss these changes. But this is just to give you an overview that you see that this is really, we can now become very concrete and ask, well, what should be the changes.
And
so
why does many worlds violate Q?
Why it doesn't, or why it doesn't?
Violate
So why it does, I will just explain this in a minute. This will be the first point I will actually explain. So maybe just one thing I should also say, if they violate this, all these interpretations, let's take for example cubism, they violate C, but of course they don't want to give up C completely. They would not say, oh, C is just a bad assumption. They would somehow try to say C is maybe not as general as it's written here, and we should add certain conditions under which C is still applicable. So that's what people say. And indeed, if you remember, so just as what I mean by these conditions, the following. So maybe if you remember the setup we had here, by the way, ask me why I called these guys F and F bar. Actually, the short answer is just I build it up from the Wigner's friend experiment, and first I only have F and Wigner, and then I add people. That's why they have bars.
Right, but it's always the bar ones that are on the left. And the
Yes,
bar ones on the right.
yes, but this is just because kind of Wigner started with the right-hand side, so to speak. So if you want to see Wigner's experiment as a special case, then ignore the bars. That's the reason.
Okay.
So okay, so there was a measurement applied to here to do F bar by W bar, and the measurement applied to W, and this was the time went from left to right. And now you see there is a measure. So some people, for example, say that F bar should not follow this rule because F bar is later going to be measured. That's what people say. But now, of course, you have to be a bit more precise. What does it mean that F bar is going to be measured? Because at the end, the measurement is, after all, again, just some unitary. So to call this a measurement only makes sense if you really distinguish fundamentally measurements from unitary. So you can say, of course, here, rather than saying this is a measurement, you can say there is some complicated unitary U going on. And now this complicated unitary we will also have in usual situations, because let's say if I'm H and F bar and I just turn my head and look in this direction, probably this is a very complicated unitary going on in my brain. So I have to distinguish this complicated unitary from one which I would call a measurement, and then say if it's the measurement unitary I don't apply this rule, and otherwise I do. So you see, you're going to run into so it's not clear how to weaken these things in a way which still captures usual situations, but that's what people try to do. And some people are now really actively working on that. For example, Chris Fuchs is trying to find a weaker version of this for cubism. So this is what was now again just the overview. Now we'll start with a discussion and answer the questions that were there. But yes, I can also answer.
Then you can consider the measurement as a unitary, because if it's a projecting measurement, it can
Aha.
transform from a mixed state
Yes.
to a pure state.
Are you asking why? Okay, this is a good question. So why can I treat this measurement as a unitary? This again, of course, depends on the interpretation. A collapse person would say, no, it's not a unitary. Now, I now implicitly, when I said that, assumed I'm not a collapse. I'm not in this collapse series. And according to the, let's say, more common understanding we have, at least in quantum information, is that a measurement is, after all, still a unitary process on a large enough system if I include the environment. And it only looks like a projection if I trace out the environment. So when I wrote here unitary, I really meant it's unitary maybe on, I mean, this box would include the at least close environment that is affected by this measurement. Yes?
Does the ensemble interpretation belong to the collapse series?
Which one? Sorry.
The ensemble interpretation?
Ensemble interpretation. I'm not sure it's so well defined what is ensemble interpretation really is. That's a good question. Actually, I cannot answer it right now because I'm not sure these people who really think that there is really, I mean, the ensemble is just something we should think about as a way to deal with the system, or whether it's fundamental. Yes, I'm sorry, I cannot answer the question because I don't actually know people nowadays who still, let's say, work or favor this interpretation. I think this interpretation is already kind of, I mean, because we can do experiments now with single atoms and so on, it's very certain, I mean, it's no longer very, pardon? No, it doesn't rule it out, but it makes it kind of less attractive, and so I don't. Anyway, my answer is I cannot answer the question right now, but it's a very good question, and I will think about. I will have to read up what these people really think about ensembles, whether this is more a tool or maybe we can discuss it, but I cannot answer it at the moment. Okay, so let me now start with, or become more specific, and maybe I start with, let's say, the very easy case, which is the collapse here, because there it's very easy why I put it into this line. Or maybe some of you knows that. I mean, why did I say it's clear that the collapse theory should violate Q? Does anyone? I mean, what is, of course I didn't now say what is a collapse theory, but essentially the answer will be an explanation of what collapse theories are. Okay, so what collapse theories do is they want to introduce, so they take quantum mechanics as it is, but then they actually modify the Schrödinger equation. And they modify, their goal is to modify it in such a way that if you have a large system, like systems that we would typically consider measurement devices, then this deviation in the Schrödinger equation is strong enough so that it will lead to a non-unitary evolution, and essentially to an evolution which will turn a coherent state into a mixed state. So one very simple way to think of about the collapse theory is one where you would say each elementary particle has a certain small probability per unit of time, let's say 10 to the minus 15 per second, that it decays into a fixed state. So you have to fix a basis. For example, you fix position basis in space and say if a particle is in a superposition between being here and here, then there is a probability of 10 to the minus, let's say 12 or so, that in the next second it decays and will be either in this position or in this. So it will be turned into, if you describe it in quantum theory, again, into a mixed state. It's now with a certain probability here and with a certain probability here, but it's no longer in a superposition. And now, if you do experiments with single atoms, you will not notice that change, simply because the usual precision you have in experiments doesn't allow you to detect a decay that has such a small probability and distinguish it from noise from the environment that may also lead to the same effect. That's, by the way, generally the problem. To test these collapse theories, you need to exclude all possible sources of noise. But now if you have a large system like a measurement device, of course what happens is that you have really 10 to the 20 or more single particles that are now in a state that depends on the measurement outcome. So within a second, it's extremely likely that at least one of them decays. And you know, quantum mechanically, you would describe the situation as a huge GHZ state, as I called it. So remember, maybe when I wrote down these states, I said, after the measurement device shows up, the friend sees up, but in principle, I could write all the atoms individually of the friend and of the measurement device, so I would have a whole chain of subsystems of atoms which are all in one position and superposed with another chain of the other case. And so, as you know, so maybe I should write that. So I have essentially a situation like if I measure a value which can be 0 or 1, then all the atoms are either in 0 or in 1. But if only one of them decays, so if I only lose one of them, this coherent state will turn into a mixed state. So it will no longer have a well-defined phase. And that's would then explain why on a macroscopic scale we no longer have any coherence. But this decoherence would now be fundamental. It's not a decoherence where we lose something due to interaction with the environment, which is not fundamental. In this case, we could always say if you isolate the system well enough, it's still coherent. It would really be fundamental, so that the system really turns from a coherent state into a mixed state. And so I actually have to change the state assigned. So of course, the state I assign to the system will change. So in this, that's kind of implicit. I assign a state to the system and let it evolve, but this evolution will now be changed. And so I no longer get the results I get from the application of the normal Schrödinger equation. So it's a very direct way of just saying, no, this is wrong. So they explicitly say quantum theory is not the correct description, you have to replace it by a different theory. That's what collapse theories do. Yes?
So if you aren't making an explicit measurement, how do you set which basis collapse happens?
No, this is a big problem. So collapse theories, okay, you could say this is a nice resolution of this whole paradox. You could just change that and then there's no contradiction. Now the collapse theories have certain problems which, as far as I can tell, of course people may have different opinions about that, are not really resolved. And one of these problems is you have to choose a basis in which the collapse happens. Now this basis, you could say non-relativistic theories, it's fine, it's quite natural to take position as a basis, like you take the position basis. Now if you have a relativistic theory, then it's no longer clear, because now your basis choice depends on the choice of a reference frame, so it's very hard to actually come up with a Lorentz invariant collapse theory. There are some people who say they have something of that type, but this is extremely hard, and I don't think that there exists at this point a theory which is completely satisfactory in the sense that it respects Lorentz invariance. Of course you can give it up and postulate that there is an actual preferred reference frame or inertial frame like an ether. You kind of go back 100 or more years in physics and reintroduce that, and then you can have it. But okay, that's a possibility. Personally I don't find it particularly attractive, but that's a matter of taste. Yes?
What do they say about spin systems where choice of
Aha.
basis could be
Yeah, so there's not one collapse theory. There are different variants. And now typically they would really look at space as the base in which you call it. So a spin which is in a superposition is just a rotated spin, and there they wouldn't necessarily say that it collapses. So it really depends now. I mean, you can now do whatever you like. You can essentially freely choose what is your collapse mechanism. And there are very different opinions. So there's not like one natural thing that everyone would say. There are some proposals which sound more natural to me, others sound less natural, but I didn't find one that really sounds completely natural. But here you have really a choice. So the general idea is just introduce some additional decoherence which is supposed to be fundamental and not And what that is up to you, and I don't think there's any agreement in the community about that. Yes?
Sorry, but I did not follow exactly how the introduction of the decoherence leads to a rejection of the rule Q.
Aha, so maybe I didn't write enough when I wrote. So here I see that applies the Born. So what is in, please, maybe I should applies, I should have written maybe Schrödinger equation to, because first you need to find out what is the state in order to even be able to apply the Born rule. So I think I should really have written what the agent does. He applies the usual quantum mechanical evolution equation, and then he knows what is the state at a particular point in time, and then he applies the Born rule. Now what the sense in which collapse theory violate this is they, yes, so they actually violate the Schrödinger equation. They would say the state evolution is not governed by Schrödinger equation. Schrödinger equation is just an approximation which holds if I look at a small system. But if I look at a big system, for example, the whole friend, as we did, then I would say clearly now the Schrödinger equation is no longer a correct description. So the state they would assign to the system before they even apply the Born rule would be a different one. So thanks for making this point, because I should really have written here Schrödinger equation. That's part of it, yes.
Yes, in that case, in my opinion, I would not think of collapse theories as a different interpretation of
That's
standard theory, but it's
yes,
an entirely
yes.
different theory of physics.
Yes, that's a good point. I agree with it, but I would say in this case, because now we have an experiment where also here it makes a difference. You could also say these are different theories. So actually my point by saying we have now a thought experiment in which it makes an actual difference which interpretation you have, means they are not merely interpretations. They're really different receipts of how I apply the theory. So the whole point is none of them are merely interpretations that are just things you should think about and you can choose and it doesn't have an impact. It actually makes a difference in how you program your computer.
Yes, I guess you can continue to convince me of that.
Okay.
Isn't this by hand sticking in an arrow of time, violating time reversal invariance?
Yes, collapse theories, they put an arrow of time, yes. In that sense, that's right, yes. That's what they do. Which is maybe not a bad thing. I mean, that's, again, a matter of taste. Yes?
So how can the violation of Q resolve the paradox?
That's also, I should, so the violation of Q now means the following. So remember that the person here in this box made a prediction about what will be the outcome that this person measures here. But this measurement is applied on a huge system which includes the friend. So now the prediction that F bar makes is therefore a prediction about a measurement of a very big system, which we calculated, and we said whenever the spin is polarized right, then the outcome will certainly be fail. Now this was based on the fact that this system evolves unitarily. If this no longer evolves unitarily, that particular prediction that this agent makes would no longer be valid.
But isn't it really a quantitative question? In other words,
Yeah.
there's some robustness in
Mhm.
the original argument, and so if the collapse
Was slower.
sufficiently weak or only
Yes.
occurs on sufficiently
Yes.
small scale,
Yes.
you still do
Right.
the product.
Yes.
Or
So
for that matter, if it's sufficiently weak, you might be able to set up a fault-tolerant
right. Yes.
version of the
Yes.
product.
Right. I agree. Yes. Yes. Of course, typically collapse theories are set up in such a way that whenever you talk about something like an agent or a measurement, they want it to be sufficiently fast. So that's the whole point of these theories. But they, of course, get into trouble because now we have very small devices to measure, and on the other hand, we can already test the coherence on very long scales. So the range in which they can still survive as a possible theory becomes anyway smaller and smaller. But yes, I completely agree with that. Yes?
Is there a way to distinguish between collapse theories and a system that just isn't fully estimated?
No, I don't think there is a. So that's a excellent point. It's very hard to actually verify collapse theory. So if you set up an experiment and you find some decoherence, it can always be that there is a source of noise that you're just not aware of. So I don't know how you would actually be able to convince anyone that you have really excluded any possible source of noise. Maybe there is a way, but I don't see that. I mean, one thing that would maybe be convincing to me would be the following. I mean, we have very good theories about error correction in computers. Let's suppose that we actually have a big quantum computer, we scale it up, and we have an error correction scheme implemented, and the error correction scheme would be such that it can correct errors above the noise threshold, let's say way above. Let's say we know the individual gates operate at the, let's say, fidelity of let's say 99.9 with, let's say, 5 nines or so, and the threshold is much smaller. But let's suppose we now run some tests on this quantum computer and we nevertheless find that there is decoherence. Then this would really be an indication that something is very strange, because now we have essentially on the microscopic scale really convinced ourselves that we got rid of the noise by the error correction. So then it could still be that there is very strangely correlated, very adversarial noise that still causes this to collapse. But yeah, so that would maybe be an experiment that could convince me that there is a real problem with our view that there is no collapse. So in that sense, that's why I said on Monday that building a quantum computer is for me one of the most important experiments in foundations of physics. It's as important as CERN and colliding particles, because we can really test whether quantum mechanics is correct for complex systems, which we haven't tested. We just assume it's the case, but we have never tested that. Yes?
What would you distinguish between a collapse theory and if you have some kind of noise, then you can interpret the static Schrödinger equation?
Yes, right. That was, I think, the same question that was asked before, essentially. Yeah. So there's no easy way to. So
But why would you
why I should distinguish him?
distinguish it?
Oh, why I want to distinguish it, or.
Yeah.
So you see,
It could happen that you have at least a way that you can think about a collapse theory, you can think about
yes. So what I want to do in this, for example, in this thought experiment, is really to test the consistency of theories. And now, according to our current understanding of quantum mechanics, I can in principle perfectly isolate the system. Now, this is an ingredient to this thing. Now, if I have a collapse theory, this is in principle no longer possible. So therefore, quantum mechanics would not, I would not run into this problem. Whereas if I have noise, I can say, let's say if there's an inherent collapse, then I could say, my assumption that I could in principle run this experiment is already wrong, because there's an inherent collapse. So my drawing of a box and say this is a perfectly isolated box would be wrong. And of course this would have an impact, because it would really question our ability to build a quantum computer, for example. So in a collapse theory, it may be extremely hard. I mean, it depends on the type of collapse theory. But if the collapse theory was a correct description of nature, one may be very worried about whether big quantum computers could still work. It's not necessary that they don't work. It depends on the collapse mechanism, but they may not work any longer. So it would have an impact. So it makes a difference potentially. Yes?
So where does quantum mechanics fit into this list?
I deliberately didn't put it so far because this was kind of a question I wanted to ask you and see what you think. But let me come back to that. So okay, now we have done the easy case. Easy case in the sense that here it's pretty clear what happens. Let me now briefly.
Please
Yes.
ask one more question. When you say that collapse theories reject Q, do you mean that there are no cases in which collapse theories correctly calculate probability equals 1? Or do you mean that even having calculated probability equals 1 should not lead to writing in the notebook, I'm certain?
I think there are no cases where, because collapse theories are really a deviation already for individual particles. The deviation is just very small. So it's a matter of scale, as John said in some way. So even for one single particle, I could distinguish a collapse theory from a non-collapse one, at least most collapse theories. There are collapse theories which say that a collapse happens as soon as the state becomes complex, and otherwise it doesn't happen. So you may set up something where you really don't see anything on one single particle. But the usual let's say the collapse theories that are most widespread, they have the property that you never agree perfectly with the Schrödinger equation, but the amount by which you disagree just becomes larger the larger the system is. So if you would make an experiment with single spins, you would normally not be able, just because of limited precision, to see the difference. But it's there.
So in the collapse theory, you never calculate probability as exactly 1. But maybe you can calculate that the probability is close to 1. And
Yes,
you
yes, yes, yes.
Could we quantify level of certainty
Yes.
in an argument involving modified version of Q, C, and S, and still?
Yes, that's possible. And this argument that I present is in principle robust. So if the certainty is sufficiently high, so if you replace all certainty, but you're almost certain, and almost means that your error is, let's say, less than 1%, then the argument still works in some way. Of course, it depends on you. Then it's more complicated to formulate stuff, because what does it mean if I'm certain? So if you are 99.99% certain that something happens, and I'm also 99.99% certain that you are that certain, how certain should I now be about the other thing? There may be some rule, and the rule is just much easier if it's 1, because then I don't need to worry about these things. But that's certainly possible to do. It's maybe a less convincing assumption at the end, because one may then dispute what is the right way to quantify certainty. But I'm sure there is some natural way to do it.
Are we in the discussion phase now?
It seems like, but let me just put one more point and then really turn to a real discussion, or official discussion in that sense. So I would like to say something about cubism and that the thing that was just asked, boom, in mechanics. So first for cubism. So cubism, what is that? And I just take it as a representative of all these things. So I'm just taking cubism as one example. I could have taken this one, also that one. This is kind of an arbitrary choice in some way. Cubism has this idea that, maybe you remember that already on Monday, when we discussed Wigner's argument, it became clear that we shouldn't think of the quantum state as what people call ontic state, so that there is really a state of the universe if we want to make Wigner's argument run, or at least this would violate the first assumption that, or okay, maybe I should put it differently. Maybe remember the first assumption that I made in Wigner's discussion was that there is a global state of the universe and it's unique and everyone agrees what that state is. That is what people call an ontic view of the wave function. So the wave function is really there, maybe similarly to how people usually think about the electric field. It's really there. We all agree it's what is the electric field strength at a certain point. Now cubism is really kind of denying exactly that and going to the other extreme. They're saying a quantum state is just a compact way of describing what knowledge we have about the system. So in some way, when you look at these epistemic views, you usually have this picture that you have the agent and the system. And so the ontic view would be that the state is kind of here. It's part of the system, whereas the epistemic view, and this is, for example, cubism, is that the quantum state is here on this side. So it's kind of in the brain of the observer. It's just something he uses to talk about the system. And why is it called cubism? It's very similar to if I would talk about probability distributions in a Bayesian way, and cubism comes from quantum Bayesianism. I would also put the probability distribution here. So why do I put it here? I made this example before. Let me just briefly repeat it. If I toss a coin, and now look, what is the outcome? What is the probability distribution you assign to the outcome? It's probably half-half, half heads, half tails. So this is something you assign to it. But clearly, it has now an outcome, let's say heads. So this probability distribution is not a property of the system of the coin. It has now heads, there's no probability, but it's a property of your knowledge about the system. And the epistemic view is exactly that, but lifted to the quantum state. So they say that it's just an efficient description of our knowledge we have about the system. So that's essentially the idea. Now, if you take this viewpoint, then clearly, then it's obvious that, so I could now argue in that way, then Q is the correct way to argue, because they would say, if I now make a prediction, so if this agent wants to make a prediction, what he should do is really to apply the Born rule to that state that he assigns to the system. So in cubism, they explicitly say that this is a correct rule. That's just postulated. So they say that this is the quantum mechanical Born rule applies to the quantum. I mean, this is kind of how you define the state. So the state is defined in such a way that the Born rule gives you the right description. So you could also see it in the following way. What you actually want to predict, so what this agent wants to do is to predict the outcome of a measurement, let's say x. And the outcome of a measurement, a prediction about the outcome is a probability distribution. But now, depending on what basis he chooses, the probability distribution is a different one. And in principle, the agent could now have a list which tells him for each possible measurement choice, what is the probability distribution of the outcome. But this would not be very efficient because there are infinitely many possible choices of basis, and if he has to store in his brain for each possible basis choice what the probability distribution of the outcome was, he would need a lot of space. And the quantum state is now an efficient description in the sense that once you have psi, you can calculate all these probability distributions using the Born rule. So it's really, in some way, just a representation of a family of probability distributions, namely the family of distributions for all possible measurements you could do. And so by definition, the Born rule is the right thing to relate these things. So that's, and now it follows just by the argument here. So if this is a correct rule, and also cubism would of course say we can actually make predictions. So at the end, if I make a prediction, it should agree with the outcome. Then it just follows from this theorem, so to speak, that C must be violated. Now, I mean, maybe that doesn't sound very concrete if I say it follows from the theorem that C is violated, but it really turns out that if you now apply cubism to this argument, then all the individual statements that we derived are correct. All these predictions that the agents make are correct descriptions. But of course, if they now put them together, they arrive at the contradiction, so they better don't put them together. So an agent a cubist agent who knows that another cubist agent is sure that the outcome is 1 should not think he should now be sure the outcome is 1. So what this all shows is that cubism is a theory in which not only the quantum states are personal to the agent, so to speak, but also the outcomes. That's kind of the implication of that. So cubism is really is by this argument forced to take an even more extreme position and say a measurement outcome is only valid. Let's say if Scott does a measurement and he sees outcome 0, this is just valid for him. But even if I know he got outcome 0, I shouldn't take this to mean that it's actually outcome 0. It's only valid for him. And okay, actually there were long discussions with cubists about this, and this is kind of the agreement that was reached about this thought experiment, and that's why they are now trying to find weaker versions of that, which would tell us under which conditions it's still allowed to do that.
I mean, presumably a cubist could allow, any amount of chaining together of probability 1 knowledge assignments, as long as they don't involve making superposed measurements on each other's brains in mutually incompatible bases.
Yeah, that's not completely clear, because you see, okay, maybe I will come back to that in a minute. But the point is that whenever the statements you make, let's say when you combine them, is always before you did anything. So let's say it would be like I would take a statement you make and promote it to mine, and then later some strange measurement is applied to you. So I should.
Well, I think so I don't understand, cubism that well, never have. But what I think that they would say is, well, the fact that, if agent one wants to make a measurement, that creates a context that precludes talking about, this, agent two being certain of such and such, because agent one is actually doing something very destructive to agent two's brain, rotating it through Hilbert space.
Yes, yes.
Now it's a totally different situation.
Yes. Let me come back to that, because there's a specific, that's something that occurs in a so the cubists don't usually say that, but there are others who say that, and I will discuss that particular point.
Who says that?
So it's part of, for example, of many worlds, and of also the explanation why in, let's say, Bohmian mechanics, the individual agents who are part of the theory cannot apply the theory. Yes?
I'm surprised, because I thought a cubist might reject Q. Because
Why?
A cubist might say, all of my probability assignments are based on a long chain of Bayesian updating
Yes.
that originally started with some kind of uniformish prior.
Mm-hmm.
And such a chain of Bayesian updating can never end with a probability exactly 1
Aha.
for
Yeah, so that's so okay. There are certain cubists who would say a probability 1 assignment is an unreasonable probability assignment, and so there are indeed different versions of cubism. Now, what I'm referring to very specifically, let's say the variant of cubism promoted by Chris Fuchs, who explicitly says it's fine to do a probability 1 assignment, but it's again the robustness. So if you don't want to have probability 1 assignments, you could say, let's take one that is arbitrarily close to 1, and the argument is robust. So in that sense, this is not really, let's say, it doesn't change the situation drastically. Okay, yes?
So just going off that point, if a different agent assigns probability 1, wouldn't that just reflect that she has more knowledge about that measurement than I do? Like in your example,
Yes. Yes.
if I assign half,
Yes. Yes.
you tell me it's 1, then I should trust you because it's a more certain process.
Then you should, yes. So okay. So the question is, if I assign probability 1 and you assign probability 1/2, but you know I assign probability 1, what should you do? Is that the question? Yeah. So according to this rule C, you should then also assign probability 1. But the point is now exactly this will lead to contradictions. That's the point. So you shouldn't do that. That's what is the conclusion. It's strange that you shouldn't do that, because you would think that now if you found someone who is certain, and we started from, I mean, of course the assumption is we started from the same prior knowledge and so on, and we have the same knowledge about the experiment, then you should be convinced about that, but this is not the case here. Okay, now I come to this interesting thing which will answer and which will lead to the discussion you want to. But let me first ask, what do you think, where should I put in this list Bohmian mechanics? So what is Bohmian mechanics? I explained that already very briefly. It's essentially one example of a hidden variable theory. And again, I could take other hidden variable theories. There are not so many concrete ones. Bohmian mechanics is a concrete hidden variable theory. So what it does, which I explained briefly last time, is that there is the wave function that it assigns essentially to, let's say, the universe or to a system, and it says in addition to the wave function you have an additional variable. So for example, if I do a double slit experiment and I have some beam and then here the 2 slits, so here's the wall and here is a slit, here's another slit where it can go through, then so it can either go here or here. Okay, this was not a very nice drawing. So it can either go here or up or down. Then, according to quantum mechanics, the situation here is a superposition. So it's something like with amplitude 1/2 it's up, and with some other amplitude it's down. But Bohmian mechanics would now say it actually really goes through one of the 2 slits. So, but what tells us through which slit? So there is an additional variable that tells me, like there is a position variable assigned to each particle. There is someone talking. Okay. Okay, I don't know, maybe these are the Bohmians who don't agree with that. They usually are. Okay, so is this kind of broadcast, this talk, by the way, live? Because maybe there was maybe I said something wrong about some interpretation, and No. Okay. Anyway, so we have to so the physics is not only described by this wave function, which leaves open whether the particle went through the upper or the lower slit. It has an additional element in the theory. So you have, this would be psi. This would be the psi variable, the wave function. And you have an additional element which one could call x, which is the actual position of the particle. So you have two elements. So there's not only one dynamical variable, so to speak, that changes over time. So this is usually something that changes over time, of course. And you have also x. So you have the classical, like in classical mechanics, the position of the particle, which you just add to the theory. So it's like a combination in that sense of classical mechanics and quantum mechanics. And now you have the Schrödinger equation, which governs how this state evolves. And in addition, you have an evolution equation for this x. This is called the guiding equation. This is like the Schrödinger equation, a differential equation, which involves also psi. So the x, the way x moves depends, of course, on x itself, but also on psi, which kind of directs the x. And so you get an equation of motion for these two objects. And at any point in time, it's therefore clear where the particle is. And you can now generalize that to many particles and to more complex situations. But that's essentially the idea of Bohmian mechanics. Yes? Pardon?
You can justify the outcome of the experiment just seeing the interference in your result if you have this exchange position on it.
Aha. So you're asking what I can see as the outcome? Or,
Yeah, in this picture, in this
Yes.
representation that we are using, and then we are also assigning the position
Yes.
of this particle, then how I'm going to actually justify the outcome, which is just the interference.
Aha, okay. The question is, how do I still see an interference pattern? Essentially, I guess that's the question. So, yeah. So the Bohmians would. So first, I should make clear: the Bohmians would not deny. Of course not. I mean, the experiment shows that there is interference pattern still. But you see, when you actually do the calculation, you will see because this particle, the movement of this particle, is not only governed by x. So it's not only a differential equation that involves x, but it also involves psi. So because psi is, of course, still the wave function that you would usually have, which shows interference, this guiding equation will direct x towards a peak of the wave function. So that's what happens. I mean, this is something you have to calculate, but you will see actually that at the end the distribution, so what Bohmians show at the end, so this equation is chosen in such a way that at the end the probability distribution of this x corresponds to the Born rule. That's the idea. So that's the point that they kind of want to reproduce quantum mechanics. So all predictions of quantum mechanics are in some way reproduced. As we will see, not entirely as in this case, but at least in these simple cases. Okay, so this is Bohmian mechanics. Now the question is, what do you think, where should I put Bohmian mechanics in this table? So clearly, let's say I should say S is of course something they want to make prediction. Let's say, or at least except this extreme form of many words, they want to make predictions. So S is not violated. Yes?
In this scheme, is there some kind of back action on the wave function by the particle? Because aren't we sort of assuming that matter both couples to the wave function through, for example, the
no, in the yes. So the evolution. So the evolution of the wave function does not depend on x. So this is the normal Schrödinger equation. So in that sense, there is no back action. Of course, if you have a measurement, then already according to quantum mechanics, there is a back action to the wave function. So there are these normal back actions, but there's not an additional back action introduced by the fact that you have this hidden particle position. So the Schrödinger equation remains the same. The only thing you do is you add an additional element, which is this x. And this always tells you in any, so you can now take a snapshot of the world and say, what is x? Of course, you don't maybe know it, but the x tells you where the particles actually are. So according to Bohmian mechanics, each, let's say, atom or each molecule of the air has at any point a well-defined position, which is reflected by x. But the wave function still evolves in the same way as it does. So it's really a kind of combining the two views, classical mechanics and quantum mechanics.
It just seems like there could be a situation where it has either, like, if you can actually measure
Mhm.
only the position of the particle, which is supposed to agree with the wave function,
Mhm.
then I have a detector or some kind of
Mhm.
matter
Mhm.
that only couples to X, but then
Mhm.
if this is supposed to also
Aha.
cause a Born rule back reaction on the wave
Yes.
function, how
Aha,
to
so
do that
if you
without-
have a detector, then the detector itself is also an object that couples to the wave function, even without introducing X. So that's why you will have the usual. So let's say you can take any quantum mechanical scenario of a small experiment and then calculate the normal evolution of the Schrödinger equation, and then everything is right, and then you just add this X, and you don't change anything in the calculation you did before. It's really an additional information. It provides you strictly additional information, but doesn't change anything you knew before about the wave function. It's like, I mean, you could just be unsatisfied at the end of the calculation that you have a big wave function, you don't now know where the particles are, and the Bohmians now add these positions, but they don't change the quantum mechanics. Okay, yes?
How does X evolve or what things?
Pardon?
How does X evolve?
So I will now I'm not going to write down the actual guiding equation because I don't know it by heart, but it's essentially an equation that just, so you have a derivative of X, so the time derivative of X is some expression which depends on a, let's say, derivative of psi in some way, on gradients of psi.
Current that belongs to psi when you write out the continuity equation for psi.
Yes. I mean, I can show it to you later, but I don't know it by heart and I don't have it now in my notes. But this is also not important for the moment because what you need to know is just that there is some equation for that depends on psi. And how it looks exactly is not so relevant. What is relevant is that it reproduces the probability distribution that you would have from quantum mechanics. Now back to my question. So where do you think I should put this on my list? So who thinks it should be, it violates C? Okay. Who thinks it violates Q? Okay. So there's, I think, okay, there were some people who said it violates C, and the more people who said it violates Q, and this exactly reflects the picture you have when you discuss this experiment with Bohmians. There are some who say C is violated, and some who are convinced Q is violated. But okay, why this difference? So this is now interesting because it comes back to the question, what is psi? Now I have essentially an option. One option is to say psi should really be understood as the wave function of the whole universe. That's one view. And which is not the same view as saying let's suppose I'm now doing an experiment in my lab and I prepare a spin up, then the wave function of the spin is up. This is a different thing because now I just assign the wave function to the spin and not to the whole universe. And so the majority of the Bohmians, but not all of them, say that the wave function we should really use for our calculation is the wave function of the whole universe, which by the way includes ourselves. So it's just kind of, you should take an outside view and think of the universe as something that is there as an object, and you assign to it the wave function. And the equations of motion are applied to this wave function. Now by that, it's already clear you will never violate C, because now you have kind of declared that the agents should all take the same viewpoint, namely the outside viewpoint. So you kind of deny, you say the agents have no longer any role in this picture. A correct description is always from an outside perspective and not from an agent's perspective. So any agent should kind of take the same out. So any agent should think he's God and looks at the world from the outside and then describes it. And now, obviously, all agents have exactly the same formula they apply, so they will never disagree. And that's why C holds. But now again, the theorem tells you now Q must be violated. And you can now indeed do the calculation. And that's what the Bohmians did, or those who believe that the wave function is a wave function of the universe. And they find the following thing. They find indeed that if the prediction that this person here makes is not correct, because he just prepares, so in this way I explained it, he prepares essentially some state, psi, which is just the state of an object that evolves here in some way and gets at the end measured here. And so this is now, this psi here, or maybe I should call it phi, is not the global wave function. This is just the spin he prepared. So it's something he prepared and then it's measured. Now indeed what happens in this situation, interestingly, is this is really a wrong prediction. So it's just the so Bohm mechanics gives you the opposite prediction from the prediction you get when you actually now look at the actual spin you prepared. So you can once do the calculation by looking at the global wave function, then you find that this outcome will be will be okay, whereas if you do the calculation for here the spin right that you assign to it, for example, then you will find the outcome is fail. So it depends. And by the way, it depends on the timing, and the timing is very important. If this measurement here of the other person is made a little bit later than that, this is not the case in my experiment, but let's suppose we delay this measurement a bit. Then again, the prediction here agrees in both cases. So what we find is an influence that whether or not this person is measured earlier or later changes the outcome that we will see here. So you have a direct non-local influence. You could kind of use that to communicate. So this person could just say, I wait a bit with my measurement, and then, of course, you would need access to these hidden variables to communicate. But in principle, the outcome here depends on that. So this clearly is in contradiction to quantum mechanics, because quantum mechanics, in this understanding Q, is that if I prepare something, the outcome that I will see doesn't depend on anything happening somewhere else. So that's why I have here a situation which clearly violates this law here. So it's simply not that thing. And the important thing is here that I wrote here to any system. So if I wrote A can only apply the Born rule to the universe as a whole, then it would again be correct. So the critical point is this here, that according to Bohm mechanics, it's not allowed to just apply quantum mechanical rules to any system. And so this is now also a problem in kind of, let's say, in the use of Bohm mechanics, which is not yet resolved. It's an open question, so maybe I shouldn't call it a problem, but an open question. The open question is the following. Suppose I go to the lab and decide to prepare a spin up and then measure it later. Now, I'm actually not allowed to now conclude that if I measure it later, the result will be up, even if the system doesn't evolve. Because I now just assigned the state to the system, to the spin, and I didn't consider the state of the whole. Of course, I have no clue what the wave function of the whole universe is. And in particular, maybe there is also a branch in which I decided in the lab to prepare spin down. So I have actually a situation where clearly in the global wave function there is also the branch in which I prepared the opposite spin. So there is, I'm simply not allowed to do what I'm usually doing. Now, of course, I would nevertheless expect that in the usual situations it's allowed to do what I'm usually doing, because otherwise it would be an unusable theory. So one would kind of try to argue that if in normal situations it's still okay to use quantum mechanics in that way. But it turns out that this is extremely hard to characterize, because normal situations are highly entangled. I mean, if you look at the global wave function of the universe, it's probably an extremely highly entangled wave function between us even not being there and preparing the experiments in different ways. And also what happens to us is a very complicated evolution and so on. So, which we would have to distinguish from a measurement. This brings me now back to the interesting discussion, I think, because you can now say in Bohm, so I think this would now agree with your viewpoint in some way, because you would say, indeed, this prediction F makes is not correct because, I mean, you said because something here happens to the person, and that's now I'm not saying you're a Bohmian, by the way, but this is now in agreement with this Bohmian picture. Now, yeah, so there is now this open question that one has to ask. So what does it mean that I apply here some re-interference? Because if I take an abstract viewpoint on this measurement again, I can say this is a unitary. And whether it's now unitary that I should interpret that as an interference or not would depend on a view I have on what is some preferred basis and so on. So it's very hard to actually now say what is a unitary here, or an evolution which still allows me to make a prediction. So let's say, let's be concrete. I prepare a spin and I give it to someone and say, measure it an hour later. But in the meantime, I talk to you. Now this is always very disrupting to talk to you, because you always give me some new insights I have to think about. So clearly some complicated unitary happens. Now what distinguishes that unitary from one which would no longer allow me to say the spin that I prepared was a correct one? And this is, I think, not answered yet.
Well, Renato, I think it's not so much a matter of needing to choose a preferred basis as it is that later on in the very same argument, we are going to talk about, the W bar, observer as having definite experiences in a basis that is incompatible with the Hadamard basis, where you were measuring it earlier in the argument.
Yes,
for me, that's
that's correct. But you see, the question whether this prediction was right or not should be independent of whether this person now, because that's, let's say, that's a question I can ask without talking about this person. I can ask, is the prediction he makes here correct?
Then I would say that that's a different experiment. That's an experiment where we just go and ask F bar, for their opinion, right? But then in the other experiment, we're doing something destructive to the observer. Where we're actually we're interfering what you yourself elsewhere in the same argument want to say is a superposition of two different experiences of the observer, right? You're interfering them, and then that creates a different situation where the place where I part ways from you is precisely in chaining together these two different probability one knowledge assignments, from two different situations, in one of which we do this experiment that interferes the two states of the observer, and in the other of which we don't.
Yes. Okay. I don't know whether we should now lead I mean, I would have many to say, but maybe I should also take other questions, and I would be very keen in answering that, but I fear that it will, I should also take questions because there are only 10 minutes before the end, and I hope you will still have time to listen to my answer after the lecture of that. But that's yes, okay, let me first take other questions. And yes, please.
So, first of all, is it possible to simplify the experiment, identify all of the different people doing different things?
Yes, I mean, depending on, I would say this depends on the interpretation. So you see, actually it's called proposed simplification, which I think is a correct simplification in a certain interpretation, but in certain other interpretations it would lead to different. So certain things I said here so for example, let me just make the following example. So here I said in this experiment, this person prepares a state in a particular way. Now, in quantum information, you would say, oh, this is equivalent to just say these two guys are at some point entangled. So let's just prepare an entangled state and not think of this person flipping a coin and then prepare a state. But this is, and this is equivalent in the usual quantum, let's say, information theoretic view we have. Now, in certain interpretations, for example, consistent histories or so, this makes a difference, because the way you talk about a preparation of a state, let's say you apply the Born rule to it, a difference is, I mean, not all interpretations talk in the same way about the preparation of a state. So the preparation is not necessarily the same as putting an entangled state and then measuring one part. So I would agree that you can simplify it in most interpretations, simplify, change it to an analogous one, but you have to be careful, because you see, certain notions like preparation of a state and so on have different meanings in different interpretations.
I was thinking in an interpretation independent sense. The experiment led to...
Okay, then it's very hard to... Yes, but then it's very hard to do a simplification in general, because in okay, if you are independent of an interpretation...
One person who does everything.
One person. No, I don't think this works. So you see, the argument, so the crucial idea behind the argument is really that I'm talking about agents who write that. So I'm not claiming, so of course you can say these are just two entangled particles and we do certain things, and then it's like a Bell experiment in some way. But the point here is really, what I want to show is not that there is a kind of these are also different assumptions than locality and so on. So what I want to show here is really the following. So you assume that's why I stress this point about programming computers. You have a set of computers that you program with the rules of quantum mechanics, and then this is like the general view on a theory is that if I have a well-defined physical theory, could be quantum mechanics or something else, I can program computers to follow the rules. And now I can let them act in the world, and they always have to write down their conclusions, and at the end of the day they come back to me, or one of them comes back to me and shows me what conclusion he drew and what he actually saw. And if this disagrees, then one of the rules was wrong. That's kind of the flavor of the argument. Now, I cannot argue in that way if I don't have different agents, because it's really crucial that we look at the situation from agents' perspective. If you take a global view, then we can just think of a big entangled state and a Bell type measurement. So it's really about testing. So that's why I said yesterday, this is the crucial idea. We test whether agents in the world behave correctly if we program them with the rules. And that's what we do. Like, we are agents, we have certain rules, and we want to know, are the rules we are using correct or not? And the conclusion is the rules cannot be these two. That's clearly the conclusion. Now you can say it's clear that it cannot be that one because there was this and this problem, but then you have to change it. You have to say, what is now your replaced rule that we should still use?
I can't resist just asking one simple thing.
Yes, sure.
In the if you say what I said, that you just deny that you can chain together probability one knowledge assignments that involve measuring observers in incompatible bases, which of these assumptions am I rejecting?
So you're saying so maybe I should first say the
setting.
The setting is always the same. So I'm not changing a setting. They're just different agents. So, okay, I should just be clear about what do you mean by different settings. So this is not an experiment where any choices are made.
Sure.
So the experiment is always just fixed.
Sure,
everyone has a fixed.
That's fine. But,
and now,
regardless, if you say the thing I said, right, which of these is being rejected?
I would say you would reject Q, because Q was what was used to say that. I mean, you said explicitly you disagree with what you called point 3. I think that the prediction that this person makes about this outcome is correct. That's what you deny, which is something that is derived from assumption Q. Yes.
Or I could say that I'm not even sure that that observer still exists, or is he?
Yes. No, he doesn't. He doesn't exist any longer.
Yeah.
But you see. That's okay. That's also an excellent point, because let's suppose I make a prediction. Let's say I'm this person. Now I make a prediction about something which happens after I'm no longer alive. Let's say something that happens in 100 years. But somehow I make sure that the prediction I made is somehow accessible still to the world. Otherwise, there's no point in verifying it. I mean, that's the point. That's why we use C to chain together stuff so that people still know what I predicted. So if I now make a prediction about what happens in 100 years, of course I will never be able to verify the prediction, but others may be able to verify it. The question is this still now a valid prediction, or can I only predict stuff that I can myself verify? So there are people who are indeed denying that and say that Q should only be applied as long as I can myself check the prediction. And if someone else checks it, that's not valid. Then it's maybe a wrong one, even if he knows what I predicted.
This sounds reminiscent of the whole debate around black hole complementarity.
Yes, that was my, on Monday I said this is kind of a version of testing the consistency of quantum mechanics without introducing gravity.
Okay.
Yes.
No, but that's precisely the move that's made there, right? To say that
yes.
The observer is outside the horizon.
Yes, exactly, yes. That's right, yes. So with this complementarity idea, you could indeed say, although you would need to have a definition of, let's say, yes, what it means to no longer be myself and so on, because am I still myself in a minute? And then if it's too strong, this complementarity is also. Okay, yes, so there are many questions. So I hope it's okay if I just use the remaining minutes to answer questions. And I think we went through most of the things. And I will at the end give a summary. Maybe I will take a few short questions before.
This is like quantum information summer school.
Yes?
So when you told me that these agents were computers,
Yes?
and they were writing in notebooks, I thought they might be quantum computers, and
You
their
could think.
notebooks are quantum registers.
You can think of it in that way, yes. Yes. I mean, okay, that's a very good question. So I would actually implement, indeed, the experiment with quantum computers, but I would not need quantum computers who can do anything that a classical computer cannot do. So they would all be operations in one basis. But it's useful to use quantum computers because, for example, here I want to measure that computer in a strange basis, and then I can implement that much more easily if it's a quantum computer. Otherwise, I would really, because then I can just do this measurement on the logical subspace. So yes, the answer is you can think of quantum computers, but you never need an incoherent operation. So you can have a quantum computer that only does control knots and ants.
But you do need to measure in the Hadamard basis. That's
Yes, right.
clear.
Yes, right. I'm just saying if I had a classical computer here, it would be very hard to measure it in the Hadamard basis. But yes, sure, I need to measure it in the Hadamard basis. But you see, I'm never talking about what this computer is after I measured it. So I was, maybe yesterday, I was always, that's maybe what you noticed, I was always talking about times. I said, for example, this person talks about what is in the notebook of that person, and it's always at the time when this person still exists. So I never talk about a person after it has been measured in a coherent basis. That's why I was always careful in talking about times, because indeed after this computer is measured, it may be in a very strange state which I don't understand. So I never talk about situations where someone has been measured and then still talk about that person. Okay, maybe a last short question and then I will come to a summary. And
Yeah, so you touched on this a little bit, but this seems a lot like quantum evangelism in a lot of ways, to arguing which of these interpretations is right.
Mhm.
But there's got to be some sort of experiment to verify this, right? This isn't religion. And so what do you need to do, what do you need experimentally, right? You
Yes.
mentioned having, if you have a quantum
Mhm.
computer, you can figure this
Okay.
out, and you can answer these fundamental
Yes.
questions, right? But what do you need, right? Is what you need tenable?
Okay, so that's an excellent question because it just brings me also to the summary, because I wanted to say something about that. So, okay, let me actually turn the summary into an open question, kind of, because what is the open question? So let's suppose I give you the following task. The task is you are given these computers, which are agents. So let's suppose they can be quantum computers if you like, but you're only implementing classical operations on the computers, because usually agents, I mean, at least we operate classically. So you only do things in one basis in this computer. So the open question is the following. What are the rules that you should program into the computer such that if I run this experiment and at the very end ask the computer, let's say W, which is now also a computer, what do you have on your tape? What is the prediction you made? Such that, and my goal is of course that this prediction now agrees with the outcome we have seen. So I want to program computers in such a way that at the end the prediction W made, which I can read from his notebook, agrees with the actual outcome that was observed. So that's a task. You could ask how to program. What you learned now is if you program it according to these two rules, it will not work. Now, do we need to do an experiment to do that? So indeed, it could just, so what, in some way, our current understanding of quantum theory tells me without doing an experiment that these two rules will end, so at the end I will really see on my computer that the prediction doesn't match the thing. So, but did I now need to do an experiment for that? Of course it could be that I'm wrong and that indeed if computers do that something different comes out. I wouldn't expect that because you already tested. So I think we should just test quantum theory for complex systems. And if we know quantum theory is correct for complex systems, there is no need to do this particular experiment. But I think, yes, you wanted to answer something.
Not necessarily doing this particular
Yeah.
experiment, but doing what experiments can be done and what you need then to do the experiments to sort of say, well,
Yes.
this
Okay. I think the critical thing about that you can experimentally test is here when you say quantum mechanics can be applied to any system S. Any system included systems which are potentially quite complex systems. So I think what experiments should do is to test whether quantum mechanics is still valid on complex systems. We all expect that, but this has never been tested, and this could indeed not be the case. And I would also expect that we may find something interesting, because as soon as we go to very large systems, that include maybe other effects, there's a potential to see something different. So I would see these experiments as much more useful than experiments to have another Bell test with known particles. I think we should really go to complex big systems and test quantum theory there. But yes, so that would be the answer to my question. Okay, maybe to summarize now again. So as I said, I summarize it with this task. So try to think of, see this thing, my whole series of lecture, as telling you there is something to be done. And the concrete thing to be done is, what is the correct program for these agents? That's the question to you. Now, whatever you program into it, it has to be well defined. So you cannot say, oh, this thing shouldn't work. You have to replace it by something else, because of course, if you have too little standing there, the agents will just not make a prediction at all, and then you also don't have an interesting theory. So try to find tasks, how to find rules that you program into the computer such that the contradiction doesn't arise. And then once you have done that, you can see that maybe you are ending up with one of these interpretations, because in some way what interpretations are in this picture are different ways of changing these rules. Although it's not so well defined how to change them, they just say maybe they are not valid, but they don't say with what they should be replaced by. And that's in some way the open research field in quantum information, because all of them tell us, to change them, only few of them are concrete. The collapse theories are concrete. They tell us how we have to change Q. All the others are just telling us, you have to give up C, but they don't tell us with what to replace it with. And if we don't replace them with anything, then we end up with a rather uninteresting theory where we cannot make much predictions, because we need something like that. So therefore, I think, I hope I could convince you that foundations is still an open, widely open research field. On the one hand, on the other hand, there are concrete questions, and there are verifiable questions, because if you find rules, then you can test whether they work or not. Even theoretically, you can test that. You don't need to run the experiment to do that. And if you find a satisfactory and convincing set of rules that would not lead to this contradiction, then I think this would actually be a very nice result, potentially even a breakthrough, because this is, you can see from the variety of interpretations, this is really something where people simply don't agree. And that's why we have all these different interpretations. Okay, with that I would like to end. I thank you again in particular for the really many questions. I really appreciate the way this went, how interactive this whole course was. This was a big pleasure. And I wish you all the best for the rest of the summer school. Thanks a lot.